So, welcome to everybody for this new colloquium. It's my pleasure to introduce today's speaker, Assaf Shani from Concordia University. Assaf got his PhD at UCLA, and after this he was a Benjamin Pierce Fellow at Harvard, and he joined Concordia in the fall of last year. And today he's going to talk about classification using set of reals as invariants.
Thank you. Thank you for having me here, and thank you for being here. And so let me say what I mean, start by saying what I mean by classification. So sort of a motivation, informal motivation to the field of classification or equivalence relations. So informally speaking, a classification problem is some collection of mathematical objects and some equivalence relation between the objects, like isomorphism. And what is a complete classification? Well, assigning to each mathematical object some invariant, so that two objects are, say, isomorphic if and only if the invariant is the same. So maybe you take a vector space, the invariant would be the dimension, or I guess this famous classification. Oh, I see somehow. Maybe this is not what I should be showing people. A famous classification of compact orientable surfaces by their genus. So two are homeomorphic if and only if this number, the genus, is the same. So of course, there are many such things in mathematics. The question that the field I work in, I've somehow lost the field of Borel equivalence relations, which I will be talking about, deals with is how to find the possible classifying invariants for a given classification problem. So in this case, the compact orientable surfaces, the classifying invariants are just natural number. Of course, it cannot be much simpler than that. But let me give you just two more examples that show up naturally where more involved classifying invariants show up naturally. So there's these two famous results from ergodic theory. One is the classification of Bernoulli shift by their entropy due to Ornstein. So not all dynamical systems are classified by their entropy, but for Bernoulli shifts, they are isomorphic if and only if they have the same entropy. So in this case, it's a complete classification where the invariants are real numbers, the entropy of the system. And there's an earlier, also famous classification result of Halmos and von Neumann of the all discrete spectrum ergodic measure preserving transformations. Now, it's not really important, not going to be important for today what this is at all. The important thing is that the relevant thing is that there's some classification of these in terms of the eigenvalues of some operator associated to the dynamical system, and the natural classifying invariants, they are, well, the eigenvalues in this case turn out to be a countable set of complex numbers. So this is like P is the power set and Aleph 0 to be a countable power set. And so more involved invariants show up in natural classifications. So here I have the invariants of natural numbers, numerical invariants that are real or complex numbers. And then you have this case of countable sets of numeric numbers. And okay, you can also talk about countable sets of countable sets, and that's where the title comes from. But of course, so far, this is very informal. So if you just ask for a map, which is a complete classification, then the answer, or let's say with numerical invariants, the answer will always be yes, just based on kind of abstract construction using the axiom of choice or something. But we don't want to deal with that. We want to deal with only things that show up naturally in mathematics, like the genus, the entropy, the spectrum, or the eigenvalues. So to deal with natural constructions. So we need to somehow restrict the objects that we're dealing with. So restrict definition of concrete classification to something more subtle. And this is how enter equivalence relations on polyspaces. So from now on, X will always be a polyspace, so some separable topological space that the topology is induced by some complete metric. And E is going to be an equivalence relation on X, which is also assumed to be not too wild. So is an equivalence relation on X. It's a subset of X cross X with the product topology of on the product. And you can ask that it's a Borel subset of this, or more generally, that it's an analytic subset. So by definition, being analytic just means that there's some Borel subset of a bigger space, X cross Y, that projects onto E with a projection from X cross X to or cross Y to X cross X. And so, okay, so why this setup? So first of all, polyspaces, there are plenty of them. So when it comes to classification problems, if you look at countable or separable mathematical objects, you can usually set them up in a polyspace. For example, if you look at a space of all countable groups, you can put a metric on them that will make them into a polyspace, will be a separable complete metric inducing a separable topology. Same if you look at the space of all countable graphs, or if you look at the set of all compact manifolds, so these are separable objects, or also if you look at hyperspaces, so like a space of all homeomorphisms of some compact space, that will also be a natural polyspace. Set of all measure preserving transformation of some measure space, that will also be a polyspace. So somehow now we just code our mathematical objects as members of some polyspace, and the natural equivalence relations in this case will always be analytic and sometimes Borel. So the reason for that, and that's the reason to focus on analytic generally, but also many of them turn out to be Borel in practice. So say you're looking at okay, I'm not giving you the details of that, but say you believe that there is some natural space of all groups, and you look at all pairs of groups that are isomorphic. So this is the isomorphism relation between groups. Then why will this and all of the others will always be analytic equivalence relations? Because you can, isomorphism can always be presented as the projection of a bigger set. So in this case, it turns out that also you can look at the space of all functions from groups to groups. That will also be a natural polyspace, and then being isomorphic. And then you can look at the set of all group F, so that F is an isomorphism between the group to group, this group to that group. This will be a Borel set, and it will project to the isomorphism relation, which is by definition analytic. And the same for all the others. So you can always just, that's why naturally speaking is these things are always going to be analytic, and that's why they focus on analytic equivalence relations. Yes?
What's the difference between isomorphic groups and equal groups?
So they could be just different, but isomorphic. So isomorphic is just if there is an isomorphism between them, but the different groups can be isomorphic. Oh, yes. So, yes. So this is, yes, maybe this is a point. So I'm not saying that there is a natural way to present all groups up to isomorphism, like their isomorphic class on a polyspace. The polyspace codes them in some way, but then it might be that you have many codes for the same, and then you have to ask whether the two things code the same group. So, oh, sorry, I already have. Another natural example of analytic equivalence relations on polyspaces come from orbit equivalence relations. So here you have, so if you study Polish groups, so a Polish group is just a topological group, but assuming that as a topological space, it is a polyspace, then you have a Polish group acting on some space, and the orbit equivalence relation is, oh, sorry, so I should say, so there are many examples of Polish groups. For example, the circle is a Polish group. All countable groups are Polish groups when you just think about them with the discrete topology. So if they're countable, a discrete topology will give you a separable topology, otherwise not. An important group for today would be this S infinity. So you take the natural numbers of some countable set, you look at all permutations of this set with the pointwise convergence topology, and that turns out to be a nice Polish group. And generally speaking, you can talk about the space of permutations of all sorts of structures. Now, given a group, you usually study its actions on other spaces. So in this case, it would be a group acting continuously on some polyspace. The induced orbit equivalence relation is defined, well, X and Y are orbit equivalent if there is some group member sending X to Y. And again, this is always going to be analytic because you have X cross X, you have X cross X cross G. And here you look at all X, Y, G, so that G sends X to Y. And this will always be a Borel set. In fact, a closed set, if you're assuming that the action is continuous, and it will project to the orbit equivalence relation. So this is another instance where always analytic equivalence relations come in. But sometimes many times they're in fact Borel. Okay, so this is just the setup. How do we study equivalence relations on polyspaces? So here's the definition. The most important definition is that of a Borel reduction. So first of all, we have two equivalence relations, E and F, on different polyspaces, X and Y. A map from the domain of E to the domain of F is a homomorphism. So that's, I guess it's not visible. A homomorphism if it respects the relation. So it sends E equivalent points to F equivalent points. And it's a reduction if there's an if and non if. So it sends E equivalent points to F equivalent points and non-E equivalent points to non-F equivalent points. Now, the name reductions comes from the fact that it's essentially reducing the problem of determining whether 2 points are related according to E to the problem that they are related according to F. But of course, it's a meaningful reduction only if the function f that does the reduction is sufficiently nice. So we are only dealing with Borel measurable maps. So we're assuming that there's a nice Borel measurable map reducing the problem of E to the problem of F. In this case, we think of E as less complicated than F. And okay, now we just say that E is Borel reducible to F, denoted less than according to B than F. If there is a Borel reduction, and if there are Borel reductions both ways, they are Borel bireducible, and we think of them as equivalent in terms of this complexity. Okay, so let me introduce a different line of motivation to study this. So another way to think of homomorphisms and reductions, well, what is a homomorphism from E to F? Right, so it's a map from the domain of E to the domain of F, which respects the equivalence relations, meaning that it will give you a well-defined map between the quotients, Y and F. So it's just a map between the two quotients, and that the map is a reduction. F is a reduction if and only if the map between the quotients is injective. So you can think of it, oh, what are you're just studying quotient spaces, and I mean sets which are quotients of some Polish spaces by some equivalence relations, and injective maps between them. That should be familiar, just studying cardinalities. But the big difference is here is that's the definable cardinalities. So we don't I mean, the big difference between cardinalities in the usual sense that uses the axiom of choice. Here we only look at Borel definable maps. So there's only cardinalities that, we're only considering maps showing naturally in mathematics or definable in a reasonable way. And as we'll see later, the picture of cardinalities looks extremely different in this context. And so it's a sort of the definable, or in this case, Borel definable version. Wait, and I should say, so the definition is relatively recent from the 1990, but the study of definable cardinalities in set theory actually goes back many decades before, and that injected a lot of kind of intuition and knowledge into this field when it started out. And another important motivation is what I just talked about in the previous slide. So to compare the complexity of classification problems. So now the classification problems, as we said, that we can code them as equivalence relations on polyspaces, and we think of one as more difficult to classify if it's above the other in terms of this relation, in the Borel reducibility relation. So the goal is to understand Borel reducibility between equivalence relations on polyspaces, and specifically analytic equivalence relations on polyspaces. Let me know if you have any questions or anything. Feel free to stop me. So the main definition, or the objects I will talk about today, are these Friedman-Stanley jumps, which are very central in the theory of Borel equivalence relations. So let me start with the definition. E is in some equivalence relation on a polyspace X. So it was defined in that paper of Friedman and Stanley from 1989. So E is some equivalence relation on a polyspace X. X, this hyperspace, all countable sequence of members from X, is another polyspace. E plus is defined as on sequences by two sequences are E plus related if anything from the X sequence is related to something from the Y sequence, and vice versa. So in other words, if you look at the countably many E classes that appear in the X sequence, and you look at the countably many E classes that appear in the Y sequence, forget about the way they are ordered. It's the same countably many E classes. So the reason I wrote it this way, and again, from taking the point of view of this definable set theory, definable cardinality, is this is essentially the power set operation, right? If you think of E as actually the quotient space X mod E, then E plus, the quotient space of it, X to the n mod E plus, will be the set of all countable subsets of X mod E, right? Because it will just countable sets of E classes is essentially E plus. But the important thing is that it's still defined in such a way that it's coded on a polyspace. So yes, right. So the fact is that if you so polyspaces are closed under countable product. That's some fact here that is being used. And that's also why in order to remain in the separable topological realm, then that's why the natural thing is only to talk about countable power sets, so only countable sets. But of course, if you ever talk to set theorists, then you know that we like the power set very much. So of course, so this is just the power set in this context. It's very important. I'll get back to it. Another point of view, and that's how I started with, and that's the title, it's natural invariants to use for classification problems. So here's this hierarchy that comes from the Friedman-Stanley jumps. Let's start with the silly equivalence relation, just equality on the reals. So the quotient is just the reals. There's no quotient to do. It's just the equality relation. Apply the jump to that, you get two sequences of reals are related if, well, each reel on the one appears on the left, each reel on the x appears on the y, and each reel on the y appears on the x, meaning it's just two countable sets of reals and it's equality between them. But we allow identify two sequences if they just enumerate the same set of reals. So this equality plus is essentially sort of equality on countable sets of reals, but it is important to notice that if you try to do it like this, there is no natural good Polish topology on the space of all countable sets of reals. So it's necessary to do this coding, to code it somehow on a Polish space, and that's what the Friedman-Stanley jump is doing. And you can keep doing that. So you can apply equality plus plus, and that would be some natural equivalence relation coding countable sets of reals. And you can do it as Friedman-Stanley did, and you can keep on iterating it, and they prove that it's actually strictly increasing. So you have reductions going upwards, but not the other way. So this gives you more and more difficult notions of classification in the sense of Borel reducibility. The classical setting, yes, in the classical setting, but in the definable setting, no, they're actually increasing. Yes. So that's a good question. In ZFC, yes, it's the same. But it's a very different situation. In fact, okay, in ZFC, if you one example of a Polish space is the reals, right? So you should think of, you take a quotient of the reals, so it's something somehow smaller. So if you think of it in terms of ZFC, a quotient is smaller. But actually in this case, equality plus equality on the reals is essentially the simplest equivalence relation. Everything else that I'll be talking about today, in particular these, but also others, are above it. But they're all quotients of the reals. So in the context of definable cardinality, its quotients are actually bigger. But it's not that surprising if you think about the axiom of choice. How do you know that quotients are smaller? You take a quotient, so you divide an equivalent set into equivalence classes. How do you know? How do you find an injective map between? So between the quotient and the original space, you need to choose one member out of class, and then the map sending the class to the chosen member will be an injective map between the quotient and the original set. But that's a big use of the axiom of choice. So without the axiom of choice, quotients are getting bigger, and that's important. And yes, so of course, so this is kind of very intuitive, very natural in the form of like definable set theory, but these things also show up in natural classification problems. So this Helmholtz von Neumann theorem I mentioned at the beginning of discrete spectrum ergodic measure preserving transformations, right, where naturally countable sets of numbers appeared in their classification, Foreman and Louveau show that in this context, it's actually equivalent to this equality plus, to the equality on sets of countable sets of numbers. So this is not just abstract, but I mean, it's motivated also by concrete examples of classification. Yes?
So the Foreman-Louveau, what we stated before the Helmholtz-Newman, it was one direction, and then they showed the reverse.
Yes. Well, first of all, you also, I mean, of course, Helmholtz and von Neumann didn't present this as an equivalence relation on a Polish space. It was just, that's it. So one thing is to present it in this context, but also they needed to, and then they showed that the Helmholtz von Neumann theorem translates into a reduction from here to here. And then they also showed a reduction from equality plus to here. And okay, maybe that's a great question, because I'll get to it much later. I mean, I'll still tell you a lot of motivation before, but this is one example of construct. So they were studying this, and in order to show this, they had to prove a reduction from here to here. And the point of view that I will emphasize later is that how to construct reduction from equality plus to other equivalence relations is well understood. That's how we get results like this and many other similar results in the literature. But what I'll focus on today is these higher Friedman-Stanley jumps, and for which it's really unknown, and I'll present some new techniques to understand, to be able to prove that they're reducible to some other equivalence relation, to study them in terms of Borel reducibility. So yeah, an important thing here in that proof is the construction of this reduction from right to left. Okay, so another important way in which these Friedman-Stanley jumps are showing themselves. So I'll mostly talk today about equivalence relations which are classifiable by countable structures. So by definition, being classifiable by countable structures is just being Borel reducible to, meaning some isomorphism relation between countable structures. So for example, if you can, whatever objects you're studying, if you can reduce them to isomorphism between countable groups or countable graphs, then it's classifiable by countable structures. And this is supposed to be, the intention of classifiable by countable structure is to be the most generous notion of reasonable classification. If you're not classifiable by countable structures, then how can you be possibly classifiable? So for example, all of these, yes, maybe all of these are considered classification using countable structures, where the countable structures are reals, sets of reals, sets of sets of reals, sets of sets of reals, so on. And classifiable by countable structure is bigger than all of those. So let me just mention another important point of view is that, I mean, it's a theorem that the following are equivalent. You're reducible to equality, reducible to isomorphism of countable graphs or groups or some other countable structures, if and only if you're reducible to some orbit equivalence relation induced by this particular group, S infinity, so the group of all permutations of the natural numbers. And equivalently, you're an equivalence relation induced by some, reducible to some orbit equivalence relation induced by some subgroup of this particular group, which can also be characterized in terms of these are precisely all the non-Archimedean Polish groups. So it's a very natural class from many different perspectives. And the fact is that if you look at the Borel equivalence relations, then we have a picture here. So you have quality reals, and then you have is it visible what's going on here? Yeah. So these are the equivalence relations which are classifiable by countable structures. Then the Borel ones are always going to be, if you keep iterating this, and okay, so I'm only going to talk about the finite iterations today, but there are of course transfinite iterations, so you can continue this along the countable ordinals, and eventually you will be below one of those if you're Borel. So it's natural to ask like what is the first one, and these are questions that have been dealt with. So given equivalence relation which is classifiable by countable structures, we essentially want to compare it to this particular natural hierarchy of equivalence relations, which are all classifiable by countable structures. Yeah, maybe just to clarify this point I made earlier, it's good to note. So what is equality R plus as an orbit equivalence relation? So remember the domain of equality plus is that you take all sequences of reals and you identify two if, well, they are just two sequences enumerating the same set. So essentially there is this group, if there's a permutation of the index set that gives you one sequence to the other. So just to see where S infinity comes in naturally, but also all the others can be seen in this way. Okay, so please again, let me know if you have any questions. The general goal, as I said, just going backwards, is we hope to be able to tell you, you give me two equivalence relations you care about, I'll tell you, well, we'll work together, we'll figure out whether one is reducible to the other. But of course, we don't want just a list of, I don't know, infinitely, like knowing this is reducible to that, this is reducible to that. We want some general structure, general techniques to be able to deal with it, to be able to address problems more easily. So what do I mean by structure? Let me say some early results to be more clear. Okay, so here's a famous result called Silver's dichotomy. So it's as you see, this is earlier, but it's very much related. So for any Borel equivalence relation, E, either it is, so here I wrote it's below the equality, but now on the natural numbers. So so okay, equality on the reals was quite simple, but equality on the natural numbers, you just have countably many classes. So it's really, so being reducible to equality on the natural numbers just says there are countably many classes of the equivalence relation. So the dichotomy says either you have countably many classes or you're above the reals. So you have as many classes as the real numbers. So perfectly many classes. And if it looks familiar, it's essentially the continuum hypothesis. Right? So it's a version of the continuum hypothesis. Every set is either the countable or the size bigger than the size of the reals. That's the continuum hypothesis. It's okay, you cannot prove it in general, but this is something that people have been studying for many decades, proving this in definable context. So if it's not true for any set, but if the set happens to be the quotient of a Polish space by a Borel equivalence relation, then it is true, the continuum hypothesis. Okay, so in this picture, what happens is we have this super simple equivalence relation, and then the next one will be just the size of the reals, and then there's more stuff. So what comes afterwards? It turns out there is something that comes afterwards, which is called E0. So let me write it here, E0. So it will not play an important role in what I will say later today, But here it is. It's the orbit equivalence relation induced by a countable group action. So here you just have a direct sum of countably many copies of Z2. Each copy acts by permuting these two, the 0 and 1. And you get this orbit equivalence relation. Essentially, so the equivalence relation on binary sequences is this equivalence relation is on infinite binary sequences where two are equivalent if they are only different on finitely many points. And the surprising thing is that it's a bigger cardinality than this equality, but it is the immediately bigger, and everything else is above it, right? So either you are like simply one of those, everything else is above it. And so there was this very, very strong structure appearing early on in the study of this subject. And again, if you think of a classical set theory, you might think, okay, I know where this is going. What is the Cantor classification of cardinalities? You have countable cardinality, and then you have the next cardinality, and then you have the next cardinality, and then you have the next cardinality, and that's the notation Cantor used, the alephs. But in terms of Borel equivalence relations, things don't work. So that was the hope, maybe originally. We'll just understand all the possible cardinalities, and every other equivalence relation will be equivalent to one of those. But things break apart quite quickly. So, for example, let me change this picture. So it's definitely not true that the cardinalities are linear in the definable context. The relation of Borel reducibility is not linear. There are many things that are incomparable. Let me mention two important subgroups of equivalence relations. So here there are the so-called countable equivalence relations, countable Borel ERs. And so these are those induced by countable group actions like this one. And immediately there's really not known. So for example, I mean, there are many things not known here, but for example, is there any equivalence relation which would be next, at least among these, like that would be an immediate successor? So it would be strictly above this in Borel reducibility, but there's nothing in between, like what happened so far. And it's still wide open, and it's one of the biggest open questions in the field. Yes?
But this is 0, depends on each. It doesn't affect the dependent. Right?
On what?
You say stop E, either E is smaller than the real, or the real are smaller than 0.
Oh yes, sorry, that's a big big typo. Oh wow, very good. Yes, thank you. Okay, that's actually very bad. So the the worst write-up of the Harrington-Kerkis-Levaux dichotomy I've ever seen. So either E is, thank you, below equality, or E0 is below E. Yes, sorry. So yeah, everything is, so somehow up to here, we understand exactly what are the possibilities. It's either this, or that. Oh, that's horrible. Thank you. And so, but nevertheless, there has been instances, there are immediate successors of E0s that are known. So for example, there's this thing here, E0 to the power n. So you just take E0 on the space. The E0 to the power n, the domain of it will be infinitely many copies of it, and two sequences will be equivalent if on every coordinate they are E0 equivalent. So it has been proved by Hjort and Kekris that it's an immediate successor of it. So it's above, strictly above it, and there's nothing in between. It's also known that it's not Borel reducible to a countable equivalence relation, to something induced by a countable group. And then there's another big open question that has been open since 2000, whether it's true that for any equivalence relation classifiable by countable structure, essentially whether this is the picture so far. Like you can say, okay, either, so we see the two different things emerging, but maybe there is some structure still there. So maybe you know that every E, either it's reducible to some of one of these, or the reason it's not reducible to one of these is because it's above this, right? So that would still be, I mean, okay, it's not as nice as, it's not as rigid as here, but still would be quite a good structure. But it's again open in general, even though it was proved by Hjort and Kekris for abelian group action. So if it's if E is induced by some abelian Polish group, not countable group, then it is true. It is no. So the point of this is to tell you what I mean by structure and how structure could and the main point here is that by having these structural results, say you want to prove that something is above E0, then you can use this. You just show that it's not reducible to this silly equivalence relation, and then you kind of get immediately from this dichotomy that it's above here. So it allows you to study equivalence relations in practice. But also the point of this slide is to tell you that somehow, so provably there cannot be too much structure actually, but also even the structure that might still be true has been kind of open for a long time, and it's a very difficult question. So what I want to talk about today is a different kind of structure that can be proven and hopefully also useful. So let me start with this theorem of Canové, Szabok, and Zaplatal from 2013. So the structure is now, instead of trying to understand directly the structure of the reducibility, focus on the structure of all homomorphisms between two equivalence relations. So their dichotomy says the following: is some analytic equivalence relation, then either it is above equality plus. Oh, so maybe I can use this. Yep. So equality plus, I should say, is above all of this picture. It's up here. So either you are above equality plus, which, what does it mean to be above equality plus? It means that there is a Borel homomorphism which is injective on the classes, which is a reduction. Or if there is no injective homomorphism which is injective, then in fact any other homomorphism is completely trivial. It's extremely not injective. It takes a comeager set of classes into a single E-class. So almost all classes into a single E-class. A quick reminder: comeager is by definition the intersection of countably many dense open sets. So it's the topological version of sort of measure 1. And okay, that's part of where the spaces being Polish comes in. You can prove, for example, the Baire category theorem on Polish spaces that says that if you take intersection of countably many dense open sets, you get a very large set. So this is just a very common tool in the context of Polish spaces, using Baire category techniques instead of measure theoretic techniques, and that's appears here. So yes, again, the conclusion here, I mean, it's any comeager set will include many different classes of equality plus, but they're all collapsed by this homomorphism to a single E-class. Now, what I want to talk about today is how to generalize this to higher jumps. And yes, oh, I should maybe going to Antoine's question. So it's important as a just general structure theory it's an important theorem, but also it can be very useful. So the way I would like to think about it, the way I usually think about it is, if I want to prove that the first bullet is true, I want to prove that there is a Borel reduction. I don't have to work so hard. I can just find one Borel homomorphism that is not completely redundant. It doesn't send almost all classes to a single class. Then the theorem will magically give me a reduction. And it's not, of course, okay, so if you look at the timeline, it's not how they prove it, but if you look at many earlier results, you can definitely present them you can use this theorem to prove earlier results. Almost all, actually all earlier results reducing equality plus to some other equivalence relation using this kind of dichotomy, and it will, it will kind of sweep away all the technical difficulty into this theorem. It will become very easy to prove it using the theorem. And that's why I want to generalize it for the higher jumps. But there are some very immediate difficulties. So one is this important reliance on Baire category techniques. So it turns out if you look at the Friedman-Stanley jumps, so I'll write it here. So what was this equality? Oh, is it visible here? Yes. Plus 2. So plus, it's defined on the space. You take the space R and then you do 1 plus, and then you take a second plus. So you have all of these infinite, so you have this infinite matrix of reals. The idea is that this matrix of reals defines a set of sets of reals by the columns, essentially. So, but in this space, in this topology, it is the fact that, so even though the equivalence relation is strictly more complicated than the first plus by the theorem of Friedman and Stanley, all the complexity is hidden in a very small set, on a meager subset of the space. So if you restrict the equivalence relation on a comeager set, on almost all the space, you actually lose all of the complexity. So somehow it just, I mean, so okay, it might not be clear exactly why this prevents you from proving something like this, but the point is that the topology is not right for Baire category analysis like the one in the theorem. Yes?
True for a higher head?
Yes, the same argument would be true for higher. Yes, you will always go back to here, actually. And it's also, yes, I should say, it's also an issue of other jump operations. Somehow they don't tend to provide the right topology. And another issue is that there is actually a natural homomorphism, which is not a reduction. So there is no reduction from the second to the first, but there is a natural homomorphism. Maybe I should. So the homomorphism, in order to be homomorphism from here to the first jump, you need to take sort of a set of reals and send it to some single set of reals, and you can do it by just enumerating the reals like this. Right? So if you take this kind of set of reals, you essentially forget how to divide it into subsets, and you just remember, you just take an enumeration of all the reals that appear here. You can see that it's a Borel homomorphism from the second to the first. Now, it's not completely trivial in the sense, I would not expect anything like this for this particular homomorphism, that it's somehow, I mean, it's not a reduction, but it's still, it preserves some important information, like all of these real numbers. So the main result, oh yeah, so what I wrote here is, so here is this is the matrix of numbers, and here it's like the numbers enumerated using this snake enumeration. That's what this notation means. And the theorem is that you can take these into account and find a complete generalization of the result for the finite jumps. So here's the result. So first of all, the first issue was that the topology was wrong. So let's change the equivalence relation. So there's some other equivalence relation, Fn, defined on some other polyspaces, Xn. I'll tell you about them later, that are the same. So up to Borel by reducibility, they're just the same as these Friedman-Stanley jumps. But somehow this will be the right topology to work with. And there are Borel homomorphisms. So for example, from the higher jumps to the lower jumps. So for example, 2, 1 will be exactly this homomorphism that I told you about. So that these are essentially the only homomorphisms. So now it should be something like before for any other equivalence relation. But here I'm only looking at the class of, I'm only able to prove it for the class that I've been talking about, the classifiable by countable structures. So either you are above Fn, so now you have this plus 2, which is the same as F2, and then so forth. Or, so if there is no homomorphism which is injective on the classes from Fn to E, then all other homomorphisms are relatively trivial, meaning they factor through this one bad homomorphism. So maybe let me have the picture of the factoring. So I have some Fn. So I'm under the assumption that Fn is not Borel reducible to some E, and I have some other homomorphism, then not only this homomorphism is not injective, it in fact factors through some other already known not injective homomorphism, this one. So essentially it's a classification of all homomorphism, right? You can either have injective homomorphism, these are the reductions, or you're just one of these up to a commigure set. And again, this whole thing only happens on a commigure set. So you have to be able to get rid of a small subset of the domain to conclude. Okay, and again, just like before, I view this really as a method to try to prove that equality plus n is reducible to some E. If you want to prove that the first bullet holds, you don't have to work too hard. You just, to find a real reduction, you just need to find some homomorphism which is not well, which is essentially different than any one of these particularly given homomorphisms. Yes?
So is it for every K or there is a K?
For some K, yes. Oh, I see. For some K less than n. So if yes, I snuck here omega also. So omega is just there's a natural limit stage of this construction, which I'll discuss in a minute. So so if you think of it for finite n, then it's just n minus 1. It will be equivalent if you just take n minus 1 here. But then if you have here omega, then then for every f there will be a k less than omega. So that yes. So this theorem is true for all the finite jumps, but also for the first limit stage of this jump operation, which I denote here by f omega. When I will say something about it. Okay. So yes, actually, let me say something about this f omega. So yes, you might see it might seem like a very technical thing to focus on, like how to study all homomorphism up to bare category, but it does naturally imply other things that have been that are of interest just from the point of view of Borel reducibility. So let me get back to this. The omega jump is defined just as the product of all the previous jumps. So that's the limit stage, and so here's a result about the omega jump. So again, from the point of view of this theorem, it's equivalent to this f omega. And so this is actually a question that was asked by Clemens in 2022. Suppose E is, so here's the corollary of the main theorem. Suppose E is strictly below equality plus omega, so the omegath jump. Then again, something similar to before but different, every Borel homomorphism is trivial on a large set, in which sense that for any Borel homomorphism, there is a fiber. So let me actually draw this. There's a fiber so that if you look at the pre-image on that fiber, then you get the same complexity. So why, and I wrote here the terminology that Clemens used to define this is saying that the equivalence relation is regular. So if you remember about cardinalities in set theory, so kappa is a regular cardinal if whenever you have lambda which is less than kappa and you have a function from kappa to lambda, then there is a fiber, so the preimage of one point that is the size of kappa. So somehow if you divide, so regular cardinality is if you divide it into a smaller amount of pieces, then there is one piece that is as big as the whole set. And so Clemens was studying regularity in the context of Borel definable cardinalities, and he conjectured that he noticed that actually, so there's again, not everything is intuitively, not everything is analogous with the classical sense. So for example, the finite jumps are not satisfying, will not satisfy this property, but he conjectured that for the omegath one it does. But there really weren't any tools to prove this, and it follows very quickly from this. So yeah, so why does it follow? I mean, I will not give the proof, but what is the point? That since you have this strong dichotomy for all Borel homomorphisms, so we're in this case, so E is Borel is strictly below F omega. So we're in the case that we have this picture. But now we want to prove that any Borel homomorphism, something is true on a fiber, right? So there is a fiber so that something annoying is true. But now instead of having to deal with arbitrary homomorphisms, because arbitrary ones factor through these ones, you only have to prove it for this very specific homomorphism, and that's very manageable. You just do it, and that's it. So that's how this kind of dichotomy works in practice. And there's other things you can prove. So just for example, some closure properties between equivalence relations. So here's the result. Suppose you have a bunch of equivalence relations classifiable by countable structures. They're all not above equality plus n. And here, actually, I'm only looking at n, which is finite. So the question is, can you present a cardinal as a product of countable product of smaller cardinals? And so, of course, in this case, yes, right. This omegath one is literally presented as a product of smaller things. But if you look at the +1, +2, +3, it doesn't look like they could be presented. And in fact, you can prove that they cannot be presented this way. So if you have things that are not already each one of them above equality plus n, then the product will also not be above equality plus n. And again, this was known for the case n equals 1 by the same essentially proof, but using the dichotomy of Canové-Sabok and Zapletal. And again, the idea is simply that you replace, because they're equivalent, you can replace this Friedman-Stanley jump with Fn, and then you have this picture. And then the fact is that, well, factoring through this is already stronger than being not a reduction. But essentially, the fact is now that if you have countably many homomorphisms, and each one of them factors on a comeagre set, then you can find a single comeagre set where all of them factor, and that's just because being comeagre, the countable intersection of comeagre sets is comeagre. So the ideal of small sets or large, the filter of large sets in terms of topology, just like in terms of measure theory, is closed under countable operations. So do I have time? I guess I have 5 more minutes. Or, oh, 10 minutes more, maybe. So yeah, so this is some examples of how you can use these kind of nice structural results. Oh, let me also maybe mention, just to be clear. So going back to the theorem, so it really is a direct generalization of this Canové-Sabok-Zapletal dichotomy. Maybe it's not clear from the phrasing, but so what was Canové-Sabok-Zapletal was if you have some E which is not Borel reducible to equality, it's not above equality plus, any homomorphism is trivial, just sends a comeagre set into a single class, but you can present it as factors in a similar way, factors through some, so you can fix a homomorphism that just says everything to a single point in some space with one point where the equivalence relation is just equality. So sending a comeagre set into a single class is the same as this picture factoring. So you can sort of, right. So the Canové-Sabok-Zapletal picture also looks like this, where U10 is just the homomorphism sending everything to a single element. So it's really a direct generalization in some sense. And so this is what I said. Okay, so I guess I never told you what the definition, right? So somehow there were these Friedman-Stanley jumps, and then they were bad, and then there was something else, and then everything was good, and you could study them and prove these dichotomy theorems and everything. So, but what is the definition? So it's not really that mysterious. So here it is. Let me do it just for the n equals 2 case. So remember, we're trying to do something like this, sets of reals. So here's a different way of coding sets of reals. I start by just coding a set of reals, and notice, so this is just the domain of equality plus. I just have a sequence of reals, and I have S infinity acting by permuting these reals. But now the way to, instead of just taking infinitely many copies of these sets of reals, I'm just gonna take this set as my base set and use binary sequences to carve subsets of it. So this binary sequence, so I have here the space this cross infinitely many infinite binary sequences. This binary sequence will carve out a subset by, well, not including these because there's a 0, and then letting these in because there's a 1. So I have a subset that doesn't have this, has the green, has the yellow. And then here I have 1, 1, 1, 0. So I have the subset with the black star, with the red star, with the green star, but without the yellow star, and so forth. So just a different way of coding subsets by having one set and then binary sequence carving out these subsets. Now, what happens for this S infinity action that induces equality plus? Whenever you permute these reals, you also, if you want eventually to get the same subsets defined from it, then you have to make sure you permute the indexing of these binary sequences at the same time, just to keep the coding. Right? So if I change between these, so if I change between the red and the green, I also need to change this 0 and 1 in order to carve the same subset. So there's this natural diagonal action of S infinity on all of these copies of the natural numbers at the same time. And F2 is defined as the equivalence relation on this space where the action, so this blue copy of S infinity is acting just like in this picture. It acts at the same time on this copy and diagonally on all of the infinitely many copies of N here. But remember, at the end of the day, we just care about the countable sets, subsets that appear. We don't care about the enumeration of this, of the subsets as well. So we don't care, we don't care which subset appears at which point at this particular sequence. So there's another copy of S infinity permuting the indices of these binary sequences, just because we eventually want to only remember the identity of these sets of reals and not their particular enumeration. So any questions about this presentation? This is a group, a presentation of this equivalence relation as an orbit equivalence relation, where this is the action. And similarly, okay, I will not write it, but for Fn, you can see it as a product of n many copies of S infinity, just this is F2 with too many copies of S infinity. And maybe I should also mention, so this is actually an important technical point of view in the proof. So the reason this proof is actually already for like the jump from 1 to 2 is is much bigger than the jump from 2 to 3 and so forth, is because from now on, the actions will look very, very similar. But you see, for equality plus 1, there was only this one permutation of the indices. But now the action all of a sudden looks very different. You have to worry about this double action that acts here and here diagonally. It really changes the game. It's just a very, very different type of action. And now the maps, remember, there were the maps that the homomorphisms that we classify them as all the homomorphisms up to Commeagre sets. In this case, they're extremely natural. They're just the projections, right? So if I want to look at a natural homomorphism from F2 to F1, which is just equality plus on reals, I just forget about all of these subsets and just go back to the sequence of reals. So these U's have now become very, very canonical. And maybe quickly mention that already here you can see why this presentation is somehow easier to work with. So if you look at the double jump of equality, it also is naturally presented as a group action, but it will be this horrendous, right? So you have a R to the N here, R to the N here. Oh, sorry, you have a R to the N here, and the way the natural group action for it will be, you have S infinity permuting here, S infinity permuting here, S infinity permuting here. So you'll have infinitely many copies of S infinity, but then you're also allowing to permute the columns. So you have this semi-direct product of S infinity with infinitely many copies of S infinity, and it's just a more ugly object to look at. So I will not say anything technical about the proof, but let me just mention sort of a few points, major points. So I said new ideas going into the proof, meaning that, as I said, it's really a generalization. So everything that was in the Canova-Sabo-Zapetal proof has to also be a part of it. So it really, all of it appears. But the main new ideas is this action, right? So at the end of the day, the proof, as I said, the way that the dichotomy is used is we build some f, we show that it doesn't factor through this, and then the theorem gives us magically a reduction from Fn to E. So the theorem has to build reductions, but before you only had to worry about this action of S infinity on this space, but now this action is very different, and just you need a really, I mean, the construction that dealt with the n equals 1 case, if you try to repeat it, it will not be invariant under this action because you have like the previous copy interfering with the next copy of S infinity of the action. So you really need a different construction to have invariant, so just to build on homomorphisms from these equivalence relations to other equivalence relations. Okay, there's also a technical issue of this is called Vought transform when you have a group action, a Polish group acting on a Polish space. You take a Comigr set, you ask what is the set of all of members that for a Comigr set of group members, they are being mapped into this particular Comigr set. This is a very important technique that appears in the study of Polish group actions or in Borel equivalence relations. So now, in particular, you will have to study Vought transforms for this particular action, which is different again, the previous one. But there's another aspect of the proof that really doesn't appear in the n equals 1 case, which is kind of annoying, which is this one. So it seems in order to somehow use the, I mean, there needs to be some sort of inductive step where in order to prove the dichotomy for Fn, I have to use the dichotomy for the lower cases. And I need to prove the following lemma, which is given some equivalence relation E classifiable by countable structures, if I have a homomorphism from Fn to E, so I already have these are the UNs, the UNKs, the homomorphisms from Fn to the previous ones, then I can present it this way as just a sequence built up step by step, where there are homomorphisms from Fnk to some Ek, and that this whole picture commutes on Comigr sets. So this will be completely false without throwing away some small subsets of the domain. Right? The homomorphism from Fn doesn't have to respect at all like what F2 is doing here. But the fact is that it can be done on Comigr sets. Again, it's very sensitive to the particular choice of Fn to have the correct topology and so forth. And yes, so that's also something that, and that's actually the reason why, that's the part that I only know at the moment for equivalence relations which are classifiable by countable structures. So these kind of things are maybe difficult to prove in general. Okay, so I should stop here. Thank you.
Thank you very much for the very nice talk. It's now question from the audience.
So this construction of the Fns, do you need to be careful that on your sequence of reals, every real is taken by at least one of your sequence of indices?
Wait, which construction, in here or in the previous? Or in the dichotomy?
This one.
Yes.
So for example, you need to take precautions that the green real number, there's at least one of the sequences which has a 1.
Oh, yes. So I lied here a little bit. It's actually, I mean, in order to make it a group action, I mean, this is heuristically, this is the point, but it's actually going to be the subset of essentially what you're describing. So I will want none of these sets to be empty, for example, and these kind of things. I will also want, there's some other, I mean, minor things to require here. So it's going to be the subset that satisfies that if you have two reals here that are equal, say two greens, then I would want all of these to also agree and these kind of natural things. In any case, it's always going to be a G delta assumption. So, I mean, all of these particular assumptions are necessary to make this a good and well-defined group action. And I mean, to do the right thing, to code sets of reals, they're going to be all dense G delta, so Comigr conditions. So the actual space is a dense G delta subspace of X2. Yes, but you're precise, correct.
Are the U, should I think of them as union? And this is why
yes.
U.
Oh, yes. Yes, U is the union. So here it's the union where you take all of the sets and you only remember which reals appear. So essentially you took the union of those. And yeah, so it's the natural map of the union from this power set to the previous. Just you take a bunch of subsets and you look at the union and you get a set of the lower rank. Thank you.
Happens at higher level.
Yes, so I mean, I definitely believe that. Okay, I guess I have here a slide with the open questions that I didn't just left here. So that was my first one. So it definitely should be true that there are similar dichotomies for all the transfinite jumps. And again, this will naturally answer all sorts of questions like similar questions of Clemens on the higher jumps. But it is, so at the moment, I don't have anything. I mean, it is provably more difficult. So there are I can convince you. So actually, any attempt, natural attempt that you will try to present equality plus omega plus 1 will not be the right topology. So if you just do the Friedman-Stanley jump to the F omega here or something like that, that will not be the right topology. And I do have some good topologies to work with, but all of a sudden the situation becomes complicated in the sense that it's not canonical anymore. So yeah, I should say actually all of these things, I mean, the proof is also a little lengthy, and for a while I was a little kind of discouraged to even write it. But then the reason I was not less discouraged is that there's some, at least to me, I feel like these results are very optimal in a sense, right? There's very feeling of canonical objects, right? Fn, I mean, the Friedman-Stanley jumps are canonical objects, and Fn are very canonical ways of representing the Friedman-Stanley jumps on polyspace. So it seems like very minimal, very canonical, very optimal. Now I do have some good topologies for plus omega plus 1, omega plus 1, but I have 2 of them, and none of them looks better than the other. So I really don't know which way to go, and so which way will be the right way? And it could be that there are different generic, I mean, theorems, dichotomies that for both. And the question is which will be more useful for application. It's just it just becomes a little complicated. And yes, it's also related to the fact that earlier in the field, right? So the results. So the earlier techniques on dealing with these Friedman-Stanley jumps have all been either with forcing or with determinacy. So somehow it really is an issue to deal with it in terms of bare category.
Your FNs are really nice. So they satisfy these better properties than the actual Stanley-Friedman jumps. Are there any properties of the Stanley-Friedman jumps that the FN don't satisfy, or?
Well, so only one, which is the fact that the Friedman-Stanley jumps, they come naturally in this iterative. So there's just, so you don't have to, I mean, so the only thing that's not nice here is that I had to like, for each n define it. Okay, there was some uniformity, but I already told you that actually the uniformity breaks at omega, and like the same thing doesn't work above that. So the one thing that, the reason that the Friedman-Stanley jumps have always been studied as the Friedman-Stanley jumps is there's one operation, the jump operation, and everything is just defined in terms of this operation iteratively. So that's the issue here, that it's not the case. So for example, if you can find a jump operation that somehow, it's the same as the Friedman-Stanley jump in terms of Borel complexity, but actually gives you the better topology, then maybe you can just iterate that one and actually get the dichotomies all the way, right? So at the moment, there's this annoying thing where it's not even clear if it is possible to find, to present them as a result of some jump operation. So that's the one thing that really still, yeah, it's still good about the Friedman-Stanley jumps, that it comes from a single operation that is very well motivated, well understood, of interest.
Then I could ask a very short question. You were saying that this equal R plus is equivalent to the eigenvalues of
the first one, yes.
And I mean, you literally just how do you do it? Is it a difficult theorem, or you do it by hand?
Well, so it's this Halmos von Neumann theorem, which is not very easy. Right? So it's the paper of Halmos and von Neumann from the 40s, I think.
Okay, no, but once I know that it's parameterized by sequence of complex number, it's just I cut it into real and imaginary part, and
so yeah, the difference. Yeah, so the difference between
is it, because to me it looks simple.
Yes,
so maybe there is not.
So the difference between reals and complex is not important. Is minor. So there is a bijection between R and C, which is Borel. Yeah. So I hit this, but so there's a fact that we have a classification of polyspaces. All uncountable polyspaces are equivalent, meaning there is a Borel map between the two polyspaces, which is bijection. So if you can do it with complex numbers, you can do it with real numbers. So that's
that's the theorem.
Yes. Well, I mean, as Antoine said, there's more going on. You also have to build a reduction from here to here, and there's more. But yes. So there's a lot I didn't say here, right? So there's really a lot, and this field, since the these definitions I mentioned in 89 and 90, the field really exploded in terms of activity and papers and people interested in it. But the reason to be so focused on polyspaces and their quotients by equivalence relations is because without the quotients, we understand polyspaces. So there's been 100 years of the Polish school of the Polish mathematicians that have studied polyspaces and subsets of polyspaces. And really, this is really completely very well understood. And the really novel part at the last 35 years is the quotients, that they're still pretty far from being completely well understood.
Okay, if there are no other questions, let's thank the speaker again.